Okay, hi everyone. Welcome back to our Calculus 3 class notes. We're on page 72. And now we're going to be talking about absolute maxima and minima on closed bounded regions R. So this is similar to like if we have a closed interval in Calc 1 where they're a function of one variable. But we have to figure out all the interior points of R where f may have a local maxima and minima and evaluate f at these points. So these are the critical points of f. And then we have to list the boundary points of R where f has local maximum and minimum and evaluate f at these points. So this will also be critical points but on the boundary. Look through the list for the absolute maximum and absolute minimum values of f. Okay, so it's very similar to where you check all the critical points in the inside of a closed interval and then also check the endpoints, except now we have to check this entire boundary. And we don't have to check every point on the boundary. That's an infinite number of points. But what we do have to figure out is where there's local maxima or minima on the boundary and then check those points. So let's run through an example. Example 68. Let's find the absolute maximum and minimum values of the function f of xy equals 2 plus 2x plus 4y minus x squared minus y squared on the triangular region in the first quadrant bounded by the lines x equals 0, which is the y-axis, y equals 0, which is the x-axis, and the line y equals 9 minus x, this guy. So we have this triangular region. Okay, so the first thing you want to do is see if there's any critical points in the interior of that domain. So we set the first partial with respect to x, and the first partial with respect to y equals 0. So we get 2 from this guy minus 2x. We get 2 minus 2x equals 0, so x equals 1. And the partial with respect to y is going to be 4 minus 2y set equal to 0, so y equals 2. So we have f of 1, 2. So 1, 2 is right here. So f of 1, 2 is 7. Okay. So we're just going to list all the values of all the critical points, and then we'll pick the biggest and the smallest to be our absolute maximum and absolute minimum. We do not need to use the discriminant when we're looking at finding the absolute maximum and minimum of a function over a closed bounded region R. Now we have to check all the boundary points. So we have 3 line segments we got to check. So I labeled the corner points. I labeled O, the origin, which is 0, 0. I labeled A, the point on the x-axis, 9, 0, and B, the point on the y-axis, 0, 9. So these are the corners of our domain. So I'm going to look at each piece of the domain separately. So on the line segment OA, notice on the line segment OA we have y equals 0. So f of xy is just f of x 0, which is 2 plus 2x minus x squared. So it's really just a function of x on the interval 0 to 9. So now this is like going back to Calc 1 where I have to find the critical points on the inside of the interval 0 to 9 of this function g of x. So take g prime of x, I get 2 minus 2x equals 0, so x equals 1. So here's a critical point on this boundary of the domain at the point 1, 0. So checking endpoints and the one critical point gives g of 0, which is f of 0, 0, so that corner point, that's 2. G of 1 is f of 1, 0, which is this critical point, which is 3. And g of 9, which is f of 9, 0, is this endpoint, which is minus 61. So now I kind of go through the same thing on OB. So in the line segment OB, x is equal to 0. So my f of xy is f of 0y, which is 2 plus 4y minus y squared when I take all the x terms out, where x is 0. Okay, so then that is now a function of y on the intervals 0 to 9. So I can treat this as a Calc 1 type problem. Take h prime of y, set it equal to 0. I get y equals 2. So I need to check the two endpoints, 0 and 9. Of course, x is 0, so that's the point 0, 0 and 0, 9. And the critical point on the inside of that closed interval, y equals 2. So in other words, that's the point 0, 2. So I check all 3 of those. Now I've already checked h of 0 actually, because that's f of 0, 0. Don't need to check it again. H of 2 is f of 0, 2, which is 6. And h of 9 is f of 0, 9, which is minus 43. Okay, so then on the line segment AB, which is the line y equals 9 minus x, I then substitute in f of xy for y to be 9 minus x. So I plug that into my f of xy and I simplify it as much as I can. And notice now I have another function of just x. I'm going to call that k of x. and that is on the interval 0 to 9. Okay, so I'm going to find the derivative of any critical points on that interval 0 to 9. Set it equal to 0, so I end up with x equals 4. So when x is 4, y is 5, so that's the critical point that's the critical point 4, 5. So now I'm going to check the endpoints and the one critical point. So k of 0 is f of 0, 9. I've already checked that, which is the boundary there, and k of 9 is the other boundary, which I've already checked. So I just need to check k of 4, which is f of 4, 5, and I get minus 11. So if you go back to our domain, I've plotted all these different points that I needed to check. You can see that I've checked them all. Now I'm going to list all their values. So as I list all their values, I got 7, 2, 3, minus 61, 6, minus 43, and minus 11. So the largest value I see is 7, so that's the maximum. And that's assumed at the point 1, 2. And the minimum, the smallest value I see is minus 61, and that's assumed at the point 9, 0. So if I look back here, the maximum occurs at this point, and the minimum occurs at this point. So I just did, I said, let me try to draw this. Someone to try and draw it by hand. So if you go back to this function, it is right here. It is a paraboloid. It's an upside down paraboloid. So I just did my best to sketch it right here as best I can do. So this is the maximum at 127. I've tried to cut it off on the domain. So this is the domain, the triangular region in the xy plane. Now for me to draw this really good, I actually put x this way and the positive y pointing into the paper. It was just easier for me to see how to draw that. And so you don't typically see it that way. It's still the right hand rule, but I just wanted you to, it was easier for me to see how to draw it, and it's still not easy to draw. So it's the best I could do.